the influence of preparation. Next one.
Thank you, Mr. Chairman. Hi, my name is Kibu Devji. I come from Institute of Applied Mechanics with the Aalborg University, Germany. And I would like to show some results of simulations which we have performed in ADAPCRACK3D. Let's first have a look into the agenda of the presentation. We'll start with a small introduction of ADAPCRACK3D, then we will see in detail the architecture of ADAPCRACK3D, where I can explain how a model can be simulated in ADAPCRACK. Then I will present the results of two simulations which we have performed in ADAPCRACK. One is a bicycle stem, which is mechanically loaded, and one is that of a vice trailer, which has mechanical and temperature boundary conditions. I will end the talk with a small summary and outlook. So, what is ADAPCRACK3D? It's a numerical practical simulation software which was developed in the Institute of Applied Mechanics in the University of Aalborg, and it's still under development. We use finite element method to calculate or to do fracture mechanical evaluation. In the past, we have successfully simulated with various real-time models, like you can see on the right top. It's that of a broken railway spring wheel. There was an accident happened in Germany, and this is the simulated model in ADAPCRACK. And to the left, this is that of a hydraulic press, and the simulated model in the middle. So this is the complete structure of ADAPCRACK3D, and it basically consists of two modules, NetAdapt3D and NetCrack3D. So NetAdapt, we do all the mesh adaptation work. So NetAdapt will remesh the model for every step, and NetCrack3D does all the fracture mechanical evaluation. The user can give the finite element model to NetAdapt along with the crack surface. The crack surface will give information about the shape of the crack and the position of the crack in this FE model. And NetAdapt3D will generate a global model with the crack open. So this is just a crack surface, it's not an open crack. And it will also create a submodel only on the crack front. Both these models will be later simulated in Abacus, and the results will be taken by NetCrack3D. NetCrack3D also obtains material data which we take from experimental investigations, and using both these information, NetCrack3D does all the fracture mechanical evaluation, like calculating stress intensity factor and so on. If the crack can move forward, it will send back the newly calculated crack front nodes or the coordinates back to NetCrack3D, where it will create the global model and the submodel for the following step. So as soon as a termination criteria like a fracture toughness of the material is reached, the simulation will break. So let's have a look into the simulations which we have performed on a bicycle stem. One of my colleagues, Jan Peter Bogerman, he does work on his developing lightweight and strength optimized structures using additive manufacturing. And he also developed and optimized various parts of a bicycle, like the crankset, the crankshaft, and the bicycle stem. The model which we see here, for example, is the final optimized model after several procedures, and I have selected this to be simulated in ADAPCRACK3D. According to the German industrial standard, ISO 4210, there are various cyclic and static test methods which have to be performed on a bicycle stem so that it will be able to withstand all the force. So it can be a bending and pull, bending and torsion. And among all these cyclic and static tests, the cyclic ones are the more critical ones, and among the cyclic tests, the anti-phase loading is the more critical one. So you can see here there is a high maximum principal stress as compared to the one on the left. So we have chosen the anti-phase loading to be tested in ADAPCRACK3D. So at the position, we have to, at the position where the maximum principal stress is at its highest value, we have to initiate the crack. So we have initiated a semi-circular crack. This is the form of the crack and the position of the crack. And we have meshed the model and given to ADAPCRACK, where ADAPCRACK generates the global model. This is the global model which is generated in the first step with the crack open, and then there will be a submodel which is on the crack front, which looks like this. So after I think 48 simulation steps, the simulation is open, and we can see the initial crack, the crack growth, I think after 20 steps, and the final residual force fracture here. The residual lifetime which was calculated by ADAPCRACK was 264,572 load cycles, where we are not considering the crack initiation lifetime. We have done the same simulation in Fine 3D just to evaluate how good our software is. So yeah, so you can see the initial crack, the crack growth and the residual force fracture here. Also the lifetime which is around 47,000 cycles more. And again, my colleague and Peter Rugerman have done experiments on product bicycle step, and you can see the crack initiation place, the crack growth, and the fatigue crack growth and the forced crack surface are nearly the same. We hope that there is little difference in the forced fracture surface. That's why we have a different lifetime. So that's how generally we do simulations in ADAPCRACK3D, and that's only with mechanically loaded models. We thought of adding a new option in ADAPCRACK3D just to simulate models which has a temperature boundary condition. So how can we do that? So the user given every model will be simulated in Abacus in the beginning before sending it to the ADAPCRACK3D, and we will get the temperature distribution on all the nodes. So that is the result which comes from Abacus. So that will be returned to the global model which ADAPCRACK3D writes in every or creates in every step. And this pre-simulation is carried out only once. We can use the result for all the following steps, because in Abacus, if we can use the option of interpolation, Abacus can calculate the temperature on each node on the global model for the following steps. So we just need to do this simulation only once. So the simulation procedure goes on as I have already explained, only with the new temperature distribution on all the nodes. So let's have a look into an example of a vice strainer. So vice strainer is generally used in pipelines where it can withstand high pressure and high temperature. So our model looks like this, where we'll have a pressure or a higher temperature in the inner surface and a lower temperature on the outer surface. And we have simulated with two different initial cracks. The crack labeled as 1 is at the position where a company have contacted the institute saying that they have found an initial crack here, and the crack labeled as 2 is at the position where the maximum principal stress is at its highest value. So we have done 2 sets of simulation for both these cracks. So for both these initial cracks, and one is only with pressure. That means we will have just the inner pressure on this surface, and one with pressure and both the temperature boundary conditions. So before moving to the results of ADAPCRACK3D, I will show some or few simulation results. So this was only with pressure, and you can see the inner surface is having the maximum principal stress with its highest value. And when you check the temperature difference, you can see that from inside to outside it's decreasing. And when you overlap both these, you will get a higher or more deformed model in the end. And the maximum principal stress is also in the same position but with a bigger area. So this is for crack number 1, the results from crack number 1. And we had actually, the initial crack was parallel to the side of the vice strainer, and it was always trying to orient away from that. And for all the simulations, the material which we use had fracture toughness high enough so that the crack will go till the outer surface of vice strainer. So we just wanted to learn how the crack goes if there is only temperature and if there is only pressure and if there is both pressure and temperature. But the orientation, we can see there is much higher difference, and on this case, the crack reached the outer surface faster than only with pressure. So this is for crack 2. I have 2 videos. So that is without temperature, that's only with pressure. And the crack was going forward, and even if one node reaches the outer boundary, it was still continuing moving forward. I mean, the crack along the side was going forward. But in case of pressure and temperature, we cannot see that. We can see only as soon as one node have reached the boundary, the program of the model will break, or simulation will break actually. So there is a high difference in how the model behaves if we have pressure and temperature boundary conditions. So it broke as soon as the first node reached the boundary. So to sum it up, ADAPCRACK can now simulate models that are having mechanical and temperature boundary conditions, and as you can see, there is a high difference when there is only pressure and when there is temperature which is very low. So we have not done any experimental evaluation. We are planning to do maybe in the future more experiential evaluation to validate our results. Yeah, to sum it up, we have seen the architecture of ADAPCRACK3D, then we have seen the simulation on bicycle stem, where we have concluded that the place of crack initiation, the crack path and fatigue and force fracture surface looks almost same. And in addition to that, we have we have improved ADAPCRACK3D so that it can simulate thermal stress as well. So some other developments which we are planning to install or implement in ADAPCRACK3D is that of including the crack initiation lifetime. So so that we can get the complete lifetime of the structure. Then also at present we were only looking to proportional loading conditions like temperature and pressure, but we are also planning to improve it by using non-proportional loading condition. But we have to do various experiments to find out how the crack will behave in case of mixed mode loading situations. Yeah, that's it from my side. Thank you very much for your attention.